Today, I'm going to talk about a simple data augmentation technique called Mixup. I choose tiny reproduction as the project track. Therefore, I am going to present the experiments I have done to distill and reproduce the trends in the original paper. In the following presentation, I am going to first talk about the introduction and hypothesis of Mixup. Then I will talk about the experimental setup. After that, I'm going to talk about the result and analysis. Finally, I'm going to make a conclusion. When training the models, most people will use data augmentation to prevent the model memorizing the training data. However, most data augmentation techniques require the expert knowledge to define the neighbor around each examples in the training data. Besides, the virtual examples in the neighbor shares the same class. Those data augmentation techniques do not define the neighbor relation across examples of different classes. Mixup comes up as an alternative. In the middle of this poster is the equations of Mixup. Basically, it does linear interpolation on both inputs and labels of two examples. This linear interpolation creates a new virtual examples. Mixup doesn't require expert knowledge, and it defines the neighbor relation across examples. There are several hypotheses of Mixup. Mixup can improve generalization and reduces memorization. It can improve the robustness to label noise. It can also improve the robustness of adversarial example. Therefore, I conduct 3 experiments to evaluate this hypothesis. In all experiments, I use the same experiment setup. I use CIFAR10 as the training and testing dataset. I use ResNet50 as the model architecture. I use stochastic gradient descent with momentum and weight decaying as the optimizer. I train a model with 200 epochs. I set the learning rate as 0.1 initially, reduced by 0.1 at epoch 100 and epoch 150. I apply standard data augmentation technique on training data, including random crop and horizontal flip. I made a comparison on the baseline performance and the performance of models trained with Mixup in all 3 experiments. I adapt an open source implementation to create 20%, 50%, and 80% corrupted label dataset to test the robustness to label noise. To create adversarial example, I use a technique called fast gradient sign method. Given an input x and label y, fast gradient sign method computes the gradient of the loss with respect to the input and adds a step of magnitude epsilon in the direction of the sign of that gradient. Epsilon is set to 1 in the experiment. The left-hand side in the poster is the result of the experiment. We can see that model trained with Mixup with no corrupted label in the training dataset achieved a 2.39% higher test accuracy than the model trained without Mixup. We can also see that models trained with Mixup have higher test accuracy in all 3 corrupted label cases. Lastly, we can see that models trained with Mixup have higher test accuracy when evaluating on the adversarial examples. In conclusion, we can see that Mixup improves model generalization even if the standard data augmentation is implemented. Mixup also improves the test accuracy when there are label noise or adversarial examples. That's all for the presentation. Thanks for listening.